All right, it's recording, Alex.
Okay, so I am going to talk a little bit about abstract algebra, eventually. And have you ever heard of that before? Probably not. I'm assuming so.
Never.
So I think a lot of people who take this class really despise it, and it's considered sort of like a class which breaks people. But I think that a lot of people who don't take the class might like it, because people who are turned off by classes like calculus and linear algebra,
Are dumb?
I don't really like these courses. When I took those courses, it was sort of like not that enjoyable for me. And the thing about all of math, until you get to a course like this, for the most part, is that it tends to be about practical stuff, like when you probably remember doing word problems and solving equations and stuff like that in regular algebra, and that tends to be the focus of the early classes. Is just trying to get a goal so you can sort of mechanically do something, and you could even probably learn that stuff by rote without having any sort of fundamental understanding of why it's important or the theory behind it or anything like that. And I think abstract algebra is the first course where this is not the case, and the point of it is not to teach you how to do practical things, but it's sort of to develop your mind mentally, and to teach you how to think abstractly and how to work in an abstract framework of ideas. So it's way different from these classes, and people who really love them and decide to become a math major may decide that they don't like math anymore when they take this class. And I think that's a lot of where the reputation comes from. But I'm actually not going to be talking about abstract algebra today, because there's some preliminary stuff that you have to know beforehand. And so right now, all I'm going to be doing is talking about set theory.
Like how to set the table, right?
No. So you haven't heard of set theory before?
No.
I think there was one country, I think Switzerland, at one point they were teaching set theory in kindergarten or something. I am looking at you. I don't know what you want from me. In one of these countries, they decided that set theory and this abstract stuff was so important that they should start teaching it in kindergarten or first grade. And because of that, a whole generation of kids didn't learn how to add and stuff like that. That's just a little anecdote. But okay, so let me start off with a definition of what a set is.
But did they learn set theory? They didn't learn how to add, but they learned set theory?
I guess. Look it up on Wikipedia or something. We're past it already. It's too late. Okay. Definition. A set is a collection of distinct objects which we refer to as elements. And I'm just going to underline a couple of things here. Elements and set. So those are like mathematical words. Whenever we say element, this is what we're referring to. Whenever we say set, this is what we're referring to. And so this is sort of a vague definition. It's not really totally mathematical. It's not built up from building blocks of logic. But I think that this makes sense, and I can draw a picture here. We have a circle is the set that has elements contained within it, like we have elements.
Oh, I thought you were going to draw a happy face.
That are all different. And let me actually...
If I connected the dots, it would be a happy face.
Draw numbers inside here. So 1, 2, 5, 7, A, E, F. We have all these distinct objects in a set, right? Does this make sense?
Yeah.
And we can't have another 5 in there, for instance, because they're all supposed to be distinct. They all have to be different. And this is what makes a set, is that the things inside it are distinct. And the way that we represent this with mathematical notation is like this. We have a curly brace, We go 1, 2, 5, 7, A, E, F. And it doesn't matter what order they're in, all we care about is what's inside. So if I were to reorder them, that would be the same set. I would say those sets are equal. So mathematically, that's all we care about is what's contained inside it. It doesn't matter how we might mix it up. Does that all makes sense?
Mm-hmm.
Okay. So there's some basic mathematical notation, curly braces, which I'm not really that great at drawing, I have to admit. This is supposed to be totally symmetric. Like maybe like this. I'm really careful. Like a bird or something, right? It's like I'm teaching kindergarten. I'm sure you've seen the curly brace before.
Yeah.
I get a little bit carried away. Okay, so
I didn't know what those were called. Curly brace. That's cool.
Curly brace, or a curly bracket.
Oh, all right.
It's like curly fries versus steak fries. The big straight bracket versus the curly bracket. Oh. I'm not sure what a parentheses is, like a shoestring fry. Anyway.
You're getting off the subject.
Okay, so I want to introduce some more notation. Okay, so suppose we have the set which is just 1, 2, 3.
Oops.
We could say that 1 is an element of that set. So that's what this notation means. 1 is an element of the set containing 1, 2, and 3. That's how we would read that off in words. And this will be useful later. It seems sort of obvious now, like you can just see, okay, 1 is inside there, so what? But what if we say A is equal to 1, 2, 3? B is equal to 2, 3, 4.
And A's a set and B's a set.
Right. So just for shorthand, we assign them a letter, right? And we have these operations that we can do with sets. One of them is the intersection. A intersection B.
And what does that mean?
What that means is that we're taking the set of elements that are contained in A and contained in B.
Oh.
So what this is going to be, so can you tell me what that is? What's actually contained inside this set?
1, 4, 3, 2.
No. The set of things that are in A and in B.
Yeah, but you can't repeat things, right? So it's 1 and
it's the set
3.
So let me rephrase that. Let me rephrase that. It's the set of things that are in A and also in B at the same time. So it's not the set of things which are in A and the things which are in B. It's the things that are in A and B together. Like 1 isn't in there because it's not in B. We only take the things that are in both.
Oh, so it's 2 and 3.
Right.
Da, 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 da. Felicia wants to say hi.
Come
Hello, kitty.
I was hoping she would meow on camera. She has a very nice mellifluous meow. Okay, could you every once in a while make sure that the recording thing is still going on there?
It's going.
Okay, because last time it cut out.
It's going. It's going.
And okay, so I introduced this intersection operation, this binary operation, and I want to focus on that for a minute, focus on these operations. So that we understand what this element sign here means. 1 is an element. So right, I sort of got off topic here. So what we could say is that 2 is an element of A intersection B. And this makes it sort of a less obvious thing because we're not just writing out what's in the set, right? So since we're representing it with letters and an operation, it suddenly becomes useful to be able to say what's in there and what's not. And then we could say, for instance, 1 is not an element of A intersection B. And it's still not really clear how that's useful, but you could just trust me that having this sort of language and having this sort of ability to talk about things in mathematical language will be useful. Does that make sense?
I don't believe you.
Well, that's good. That's
okay.
That's that's a mathematical way of thinking, because in mathematics we require everything to be proven rigorously. So I haven't proven it for you and you don't believe me, and so this shows that you have a mathematical mindset. That's very good.
But I do believe in God.
That shows that
That shows nothing.
I will refrain from comment on what that shows, so as not to offend more delicate listeners. Okay. So, binary operations. Binary operations on set. So all that means, a binary operation, is that we're going to have some sort of machine which takes in two sets and outputs another set. So it's a binary operation because it takes two things and it outputs a thing of the same kind. Does that make sense? Where we take two sets and we get another set out. And I already gave one example of that, which is the union. We take a union of two sets and we get a set as a result.
Oh.
Right? And we also have the union. Wait, did I say union before? This is intersection, and this is union. Right?
Uh-oh. You have to redo the whole thing.
No. Okay. Now let me define what the union is. Given sets A, B, given sets A and B, A union B is the set of elements in A. Why don't I say the set of all elements in A or in B? So what that means, it's a set of elements that are in A, that are in B, or that are in both A and B. That's what the word "or" means in math. It's a logical word, or. You could also say XOR, which would mean exclusive OR. That would mean that it's in A or it's in B, but it's not in both. But when we say OR, we mean that it could be in both. And so that's what the union is. The intersection, which I already showed, is exactly the same. Except over here we have A intersection B.
Excuse me.
Yes?
We need to pause this.
Okay, can you press the pause button, or is
I
there?
don't even know how to pause.
Okay, let me hit.
But
Okay, so
will you explain the upside down U and the U again, please?
right, because I made a mistake where I referred to this as the union because I just was not thinking, and you were asking if we should redo that part because it was confusing. So what I mentioned was that first of all, this is the intersection and this is the union, and second of all, you can remember that because this looks like a U, so it's going to be union, and then the other one is going to be intersection. So I think that should make it clear which one is which.
And what's the difference?
So the difference is this definition here, which is the definition of the union, is that it's a set of elements that are in A or they're in B. And the definition of the intersection is that they're in A and they're in B. And I can draw a picture of that, which may make it easier.
A big picture. Hi, Felicia.
So we have two sets here. This is called a Venn diagram, which may be familiar. So on one side I'll do the union and the other side I'll do the intersection. So on this side I'll do a intersection B, and on this side I'll do a union B. Okay? So a intersection B is going to be the set of elements that are in A and they're in B. So they're going to be in the overlap. And so again, the union corresponds to AND, which you can sort of remember because it kind of looks like an A, right?
Oh, cool. Okay.
Right, so we just take this stuff in the overlap. That's A intersection B. A union B is going to be the things that are in A or they're in B, which also means they could be in both. So that means we take things that are in A, that's A, and we take things that are in B. So these things in the center... Or. So these things in the center sort of get taken twice. But because we only count each element once anyway, it only exists once inside a set. It's distinct. We only take the distinct ones. Then it doesn't matter. All we end up with is everything, right? Everything goes in there once. Does that make sense?
No.
That doesn't make sense?
No.
Okay.
So A and the intersection B,
Uh-huh.
if A was 1, 2, 3 and B was 3, 4, 5,
Mm-hmm.
then you'd have the 3 in both of them, right?
Yes, for the intersection, yes. And
Okay.
So let me erase this, and we'll do that example that you just did.
But I'm wondering how the union works. I don't get how the union works.
Right. Yeah. So
Because you said that's an or, right? One or the other.
2, 3, right?
Uh-huh.
B equal 3, 4, 5. I think this is what you said.
Yeah.
And then and what you said was that A intersection B is going to equal the set which contains 3. That's
Mhm.
correct. And then A union B is going to be the set which contains 1, 2. So we take the things that are in A, and we'll take the things that are in B as well. But because we only count distinct elements, we're just going to end up with 1, 2, 3, 4, 5. So we're taking the set of things that are in A or they're in B. So what we end up with is the things that are in A and the things that are in B, which is kind of confusing, I understand. But it's sort of like, it's a different meaning of the word and. What we're looking for is we're satisfying
Oh,
this.
I get it. Everything. So actually you're doing, when you see that, it's everything.
Yes. It's because we're taking the union of A and B, we're unioning them together.
Okay.
But logically we say that an element X is in the union if it's in A or it's in B. So that's the logical way to think about it. Is this element in the set? Well, all we have to do is check whether it's in A, and then check whether it's in B. If it satisfies one of those, then it is.
I hate logic. Okay, go on. Got it.
You're not gonna like the.
Well, I remember it in a minute.
You're not gonna like the last half of this class because all of that proves.
Oh shoot! I'm not gonna like it, and I don't even know what a proof is. So.
Okay. So we did some notation. So let me just do a little review of the notation that we've done. So we have these curly brackets, and we have this element, and we have union, and we have intersection, right? There's a couple more things we need. One is going to be the complement. So we have, again, A is equal to 1, 2, 3. A complement is going to be everything that's not in this.
Not in what?
Not in the set A. So it's not 1, it's not 2, it's not 3, it's everything else.
Oh.
So what is that? That's a trick question asking what that is because we haven't said what the set of everything is, right? Like horses, candles, like
Cats.
smiley face, exclamation point, cats, you said cats. Let me see here, what else would be good? Plaid patterns, maybe? I wish I was better at drawing things and I could do that. But you get the idea, like there's a ridiculous amount of stuff that we could possibly put in here if we consider everything. So we would need to define some sort of universal set, like suppose that we only consider numbers greater than or equal to 1, whole numbers greater than or equal to 1. This is often called the set of natural numbers or counting numbers. It goes 1, 2, 3, everything all the way to infinity. In that set, and if we define a universal set like that, then A complement is going to be 4, 5, 6, right?
And on and on and on and on.
Yeah. So because we've sort of said what the universe is, we've limited it in a very artificial way. We had some arbitrary restriction on what the universe is. We're allowed to take the complement.
How do you... Complement or complement?
Complement.
Okay.
It's the complement because A union A complement is equal to the universe. So it's as complementary as you could be as if you get everything when you take the two together.
What did you just say? What equals the universe?
If we take A and we take its complement, A and everything outside of A, and put them together, we'll get the entire universe. By definition, because the complement is everything that's not in A but is in the universe. It's everything outside of A. So if we take those two and union them together, then we'll get the universe back. Does that make sense?
I have a headache. Okay, go on.
Okay. So now we have the complement. And one last bit of notation I want is the subset. So let me give a definition of that. A is a subset of B when every element in A is in B. Right? So we have two sets, A and B. And we're saying that A is a subset of B if every element in A is also in B. Does that make sense?
Say it again.
A is a subset of B if, given any element in A, we know that it's also going to be in B. An example of this would be 1, 2, 3 is a subset of 1, 2, 3, ... Right? This is a subset of this because everything in here is also in here.
Okay,
So it's a subset.
I get it. I get it.
Mm-hmm. And the way we could refer to this, the way we could state this logically is we could say that X, an element of B, if X is an element of A, that implies X is an element of B. That's just a little bit of logical notation. But that was not, I have not taught that, but a lot of people may be familiar with that notation. This arrow means that this statement being true implies that this statement is true.
What were we talking about, or what were you talking about before this? So we have subset. What was the other? Complement.
Complement. So
Okay, okay.
Mm-hmm. And okay, so now we have pretty much all the notation we're going to need. There's other notation that could be introduced, but this is like the bare fundamentals.
So one, like the complement is a little tiny C-looking thing,
Uh-huh.
and it's like pi then.
Yes, we put it, we take it like an exponent. We put it above the set.
But the other one's like a big C.
Yes, the subset does look. Sometimes it's written like this, the little line below it.
Oh.
And so there's several different ways that this is written. I'm not going to worry about that. I'll just do the most basic thing.
I like it with the little line below it.
Okay, we'll do that then. I submit to your artistic, aesthetic viewpoint.
My brain is getting
Nice.
full.
I submit.
You submit. How much more of this is there? Oh my God.
Well, okay, I'll just introduce one last thing, which is some set identities, or we could talk about the algebra of sets, and we'll stop there. I'll stop. I won't get into how we prove things or anything like that.
Oh, that's right. You were gonna do the proof.
Yeah, we can at least take a break.
And you
before
said
that.
I'd hate it.
Are we still recording there?
Yeah.
Okay, good. I'm a bit paranoid about that after the first experience. Okay. So, set identities. / algebra of sets. So, we have the one that I said before, which is if we take A and we take the union with A complement, that is equal to the universe. Well, that looks like the union, doesn't it? So I'm just gonna... Okay. That's how we refer to the universe.
Cool.
There's probably a much better way to write that. It looks
There's got to be a
fancy.
prettier symbol for the universe. Oh my god.
Well, that's fine. It looks like a weird smile or something. Okay, so this is one. And if we take A union A, that's going to equal A again. If we take A intersection A, that is also going to equal A. So if we take A and we add in all the elements that are in A, already in A, we'll get A back again, right? Does that make sense?
That's like 1 plus
Yeah.
1.
And if we look at the things that are in both A and A, we'll get A, right? So this makes sense, I hope. And so these are somewhat trivial identities here. We also have some less trivial ones, like the De Morgan's laws. That if we look at A union B complement, that's going to be equal to A complement intersection B complement. So this has a nice sort of an intuitive appeal to it, that if we take the complement of the union of two sets, we just sort of like take the complement of everything inside, including the union. If we think of the opposite of the union as being the intersection, we sort of negate everything.
Oh my god, you lost me.
But you understand when both this and this mean, right?
Yeah,
You
yeah.
take A union B complement, that's A complement intersection B complement. And in fact, this is true that these are equal. And it's not completely obvious, but it is true, and it can be shown that that's correct. And we also have the other thing, that if we take A intersection B complement, that's equal to A complement union B complement. So the intersection became a union on the other side, right? And then the other two were just complemented. So this is like a really nice thing that is so simple. All you have to do to take the complement of these two is just take the complement of each individual part. Where if we think of the complement of the intersection as being union, just like to remember it easier, that what we do. Right, so these are nice, and I haven't organized this very well. Maybe I can rewrite this a little bit smaller and put a little line here. A union B complement equal A complement intersection B complement. Okay. And we also have another nice thing, which is the distributive laws, which is if we look at A and we take the union B intersection C, that's going to be equal to A intersection B union A intersection C. I think I got that backwards.
I would not know the difference.
Okay. I think that's correct. So we're distributing this A inside here. So it's A union B intersection A union C. It's sort of like this is similar to the distributive property of addition and multiplication. A times B plus C equal AB plus AC, right? It's a very, very similar thing, except instead of multiply and add, it's union and intersection. Does that make sense?
Yes.
So this is easier to remember than it looks, and it's like it works out very nicely, even though it's kind of intimidating at first. That we can do algebra with sets really easily in a very similar way that we can do them with addition and multiplication, and it works out very, very nicely once you're sort of used to it. A intersection. We also have this B union C. So distribution also works the other way. A intersection B union A intersection C.
So why did the Swiss think sets were so important?
Well, they're sort of the foundation of modern mathematics in a way. They're used Well, we'll see in the abstract algebra course why sets are so fundamental. Or at least we'll start to see that, because they sort of underlie everything. They allow you to talk about things in a more abstract way.
It looks like a foreign language up there. Abak, baka, ubak. Unbak.
Well, I'm sure it will make a lot more sense after you've done the homework assignment, which will only take you a few hours. So make sure you do that later tonight. And yeah,
I'll ask my son to do it for me.
So there are several other identities I could write down, but those are, I think, the most important ones are the De Morgan's laws and these distributive ones. I think that is a very good start for set theory. It's sort of a lightning introduction to set theory. And the next time I will talk about how to prove things in set theory after giving a review. Okay, so we can stop recording now? I'll press that myself.
You know what? There is a problem. Okay, go ahead, stop.